Good afternoon. My name is Amy Johnston, and I am an undergraduate student in the Environmental Studies program at the University of Wisconsin-Parkside. Today I'll be speaking to you about the fluvial impacts on sedimentation characteristics and larval dragonfly habitat. Research was overseen by Parkside's Dr. Rachel Headley and Dr. Jessica Orlovsky in association with Christopher Tyrrell of the Milwaukee Public Museum. Research was conducted over 5 days from August 3rd to August 7th in Michigan's Upper Peninsula at the Huron Mountain Club. This private club is surrounded by 20,000 acres and only 30 miles northwest of Marquette. Located on Lake Superior, the Huron Mountain Club resides within 2 separate watersheds. This pristine landscape has had minimal anthropogenic disturbances, making it ideal to study. This slide maps out the collection sites. We can observe the division of watershed boundaries, outlined in blue, accompanied by the Mountain Club boundary outlined in red. Looking at the map, we are able to see the distinguished characteristics within each watershed pertaining to our chosen sites. Huron Mountain research was set to determine dragonfly distribution and breeding trends in different aquatic habitats. At each of the plotted sites, a single transect perpendicular to the flow was set up in order to collect 5 benthic invertebrate samples. Favorable habitat for the larval gomphids of interest is a coarse bedload, larger rocks, and steady flow. Dragonfly larvae attach to the bottom of submerged rocks and wood for the duration of the larval stage. Bed characteristics were observed to model potential larval dragonfly habitat while retrieving water samples to analyze ecosystem health from each visited site. To perform our research, multiple methods were utilized in the field for the necessary data that was to be collected. Data collection included a cross-sectional profile, water temperature, and discharge to record each site's flow properties. The use of a gravelometer to administer the Woolman pebble count allowed us to measure particle size distribution in our selected sites. Additionally, water quality was analyzed through nitrate and phosphate testing, dissolved oxygen, and conductivity measurements. Water samples were collected to later analyze nitrate and phosphate levels in the campus laboratory. Lastly, insect counts were observed using a Serber sampler. The Serber sampler is a tool primarily used in shallow streams and/or shallow riffle. This device is placed in linear plots along the transect. The Serber gently collects quantitative samples of benthic invertebrates as they flow into the mesh net while the riverbed is lightly disturbed. This occurs when bed particles are manually manipulated. Sampling in this manner does not cause harm to the specimens or to their habitat. Another mode of data collection utilized was the YSI multi-parameter probe. This probe is a personal favorite of mine because it records temperature, dissolved oxygen, and conductivity in real time. 3 probe readings were administered at each site. Data was recorded on the left bank, middle, and right bank for a better representation of the river's health. The next few slides will include the data analysis from the Huron Mountain sites. The first group of data comes from the Pine watershed, which, as we can observe, is home to multiple lakes. First, we will look at the Pine and Elm Creeks. Note that the grabbed pebble counts were the result of using the gravelometer. This tool measures particles from silt or clay size up to large boulders, bedrock, and woody debris. As we study the graphs, we can observe the difference in bed load between these two sites. Pine Creek exhibits a coarse bed with the majority of particles measuring 64 millimeters or approximately 2.5 inches in diameter. This particle size is comparable to a very coarse gravel that might be found in an unpaved driveway or park. Additionally, Pine Creek contains a sizable amount of woody debris, whereas Elm Creek measured close to none. The Pine Creek factors create ideal gomphid habitat compared to Elm Creek, which contains a primarily sandy riverbed with minimal pebbles of any sizable significance. The lack of rocky material at Elm Creek inhibits the dragonfly larva from inhabiting the area. Riverbeds composed of sand do not promote a larva's attachment to particles due to their small size and ease of transport. Pine Creek had also measured at an elevated phosphate level. However, that could be the cause of upstream erosion or nearby runoff. Mountain Stream has a visibly rougher riverbed. Particle size showed highest distribution between 64 millimeters and 180 millimeters. This can be compared in size to coarse gravel up to large cobble particles. The presence of gomphids informs us that Mountain Stream has a favorable ecosystem for these invertebrates. Rush Creek, however, was the most populated river for gomphid inhabitants. If we take a look at the graph, we can see the data that we do not see at other locations. This river had a virtually equal distribution between coarse sand, coarse gravel, and woody debris. Since dragonfly larvae are generally found clinging to the bottom of submerged rocks and wood, it is clear why this creek had a high abundance of gomphids. From this data, we can infer that woody debris is important to the dragonfly larva habitat. Let's move on to the salmon trout watershed. Data shows that although bed load seems favorable for larvae, both rivers had only one gomphid sighting. A physical difference for these two sites is the amount of bedrock they contain opposed to the other sites we covered previously. Excessive bedrock can deter the gomphids from breeding at a specific location or even having a successful egg to larva stage. Bedrock can increase riffle flow rate or produce rapid currents around exposed rock. This can create a hazardous and even unsuccessful environment for dragonfly larvae. On another note, the low gomphid count could be due to an elevation in recorded phosphate levels. This area houses logging sites which, given the possibility for additional erosion, can negatively affect a river's composition. High phosphorus levels can lower the water quality index while altering the chemical composition. Fluctuations can then impact a river's biodiversity. Both Salmon Trout Swinging Bridge and Salmon Trout Conway possess medium-grained, sandy riverbed particles. Though woody debris is present at both sites, gomphids were not observed nor recorded at either site. As previously stated, fine particles do not allow the gomphids to attach and anchor themselves in the water. Also, note the slight elevation of phosphorus levels at both rivers. All streams were tested for TSS, or total suspended solids. However, due to river clarity, analysis results were negligible. Nitrate results were all within standard levels as well. The photographs shown here are from the actual sites. Though some sites are absent, these pictures still represent the various riverbed sediments that were encountered. From these, we can gain a visual example of the sandy and coarse riverbeds. What we can conclude from this study is that Gomphid preference of riverbed material is important. While the presence of larvae was found in 5 of the 8 sites, not all sites met the specifications of a Gomphid breeding ground. The locations that did not contain Gomphids were made of fine to medium sand particles. From this data, we can deduce Gomphids do, in fact, prefer coarse bedload with the addition of woody debris. Out of the 4 sites that had higher recorded phosphorus levels, 3 were Gomphid-free. I want to thank you all for taking the time to listen. I hope that you enjoyed yourself, and if you have any questions, please feel free to ask. It has been a pleasure presenting for you, and have a great rest of your day.